Okay, we talked about covalent bonds now. We've introduced them, and now we're going to talk about categories of covalent bonds. Let's first look at ionic bonds, which we talked about previously. Ionic bonds are something like sodium chloride, where the electrons are all an electron has been transferred from the sodium, so it's positive, to the chlorine, so it's negative. And then we have on the opposite side of the spectrum, we have pure covalent bonds, complete sharing. And that would be something like hydrogen bonded to hydrogen. And so there's a complete sharing. They're both hydrogen atoms, so they share equally. And we did a potential energy curve for hydrogen with hydrogen. But there are cases that are in between, where you have something intermediate between complete sharing and complete transferring of electrons. Okay, and we call those polar covalent bonds. And HCl is an example. The electrons are not shared equally. They are shared, but they're not shared equally. And we have a couple ways that we designate that. So I've showed those below. Here's an HCl bond, and you use a little Greek letter delta plus to mean the positive side of the bond, and a delta minus for the negative side of the bond. So this is a delta. Delta plus and delta minus. And the minus side is on the chlorine, which pulls harder. The chlorine pulls harder on the electrons. So in other words, the chlorine is like the selfish one that while they're sharing, it's not equal sharing. The chlorine gets the electrons more often. Okay, and this is another way of showing the exact same thing. Okay, so these are identical depictions. They just give the same information. And this is a kind of like a plus sign on the end of an arrow, and the arrow points toward the negative side of the bond. All right, and we say that chlorine, since it pulls harder, we say chlorine has a greater electronegativity. Electronegativity. And that means it pulls harder, just like we said, pulls harder on the electrons. And we have a electronegativity scale, which is the Pauling electronegativity scale, to rank different atoms according to how much they pull on the electrons. So a couple things to note is the noble gases have very, very low electronegativity. They are happy with their electron configurations, and so they don't pull on the electrons much at all. You can also note that smaller sized atoms has electrons closer, and so they have the largest electronegativity. So we'll call electronegativity En. And since the smallest is fluorine, then fluorine has the largest electronegativity. And oxygen is next, largest electronegativity, and nitrogen is next after that. Okay, so in order, the most electronegative atom is fluorine, then oxygen, then nitrogen, so they pull the hardest of the elements. And we can then look at a diagram of electronegativities on the periodic table, where the height of the block tells you how electronegative something is. And so this is fluorine here, this is oxygen, and this is nitrogen. So those are the top three, and they're quite a bit higher than any of the others, and we will make a note of that later. But basically, going to the right is a greater electronegativity, and going up the periodic table is a greater electronegativity. As you can see, the low ones are in the lower left. Okay, let's try something. All right, so you use the delta plus, delta minus depiction and the polar arrows to show the direction of polarity in each of these bonds. So go ahead and stop the tape and do that, and then I will show you. If you look on the periodic table, you'll know the trends. Chlorine is more electronegative than bromine, so you put the negative that way, and you also direct the arrow toward it. But you, of course, you usually use one or the other depiction, not both. All right, hydrogen and oxygen. You can look those up, and we don't actually have to because we know that oxygen is one of the top three and hydrogen's not. But we can still go back just to check and see that we have oxygen here, hydrogen is here. So oxygen's greater, electronegativity. So we put the delta minus on that side, the delta plus on this side, and again the arrow like that. Okay, nitrogen and sulfur. A nitrogen-sulfur bond, the one that pulls harder is the nitrogen. And draw the two depictions. And nitrogen with carbon. Nitrogen, again, is one of the top ones. It pulls harder, so that's the negative. There's the positive. And the arrow would go the opposite way. All right, now, how do we know when a bond is in the polar covalent category? We said it's unequal sharing. We can actually use the numbers in the Pauling electronegativities. That last diagram would work. I also have one that's a little more legible on the next page. Oops, that's a little far. So there are numbers underneath each element on this graph. There's a 4 for fluorine. 4 is the highest. And down this corner you have 0.7. Okay, so it's basically 0 to 4. And so you can use the numbers. Okay, hydrogen has 2.1. Chlorine has 3.0. So if we want to look at an HCl bond, we have 2.1 and 3.0. Okay, I went way too fast. Okay, so let's put our numbers in. We say hydrogen was 2.1, chlorine was 3.0. So what we talk about is the difference between them. Okay, the delta. Difference in electronegativity equals 3 minus 2.1, so that's 0.9 is our difference. And so we can rank bonds according to the difference in electronegativity between the two atoms. And different texts differ on this topic, but the text we're currently using says that if the difference in electronegativity is greater than 2, then it's an ionic bond. Clearly this is not greater than 2, it's 0.9. And if it's a nonpolar covalent bond, or completely pure covalent, then it is essentially 0, although people differ on that too. Some people say it's from 0.4 and lower, but somewhere in between are the polar covalent. So they will be less than 2 and greater than 0 or greater than close to 0 will be the polar covalent bonds. All right, let's go down and look at those electronegativity values again and do some other problems. So you look at these electronegativity values and classify these bonds as to whether they're ionic, polar covalent, or pure covalent. And I've already actually done the numbers, but we can look at them. Silicon is 1.5 and chlorine is 3. Or no, silicon's 1.8 and chlorine's 3, so the difference is 1.2. Beryllium is 1.5, oxygen is 3.5, so the difference is 2. And carbon and sulfur is the last one. Carbon is 2.5, sulfur is 2.5, so the difference is 0. So we can classify those bonds. We can say that the beryllium-oxygen one is ionic. We can say that carbon-sulfur bond is pure covalent or non-polar covalent. And we can say that silicon and chlorine is a polar covalent bond based on the difference in electronegativity.